Alright guys, I'm back to fill in the very end of what I was trying to say about topology in our class. Ran out of time again, but I just wanted to finish up briefly. I appreciate you taking the time to watch this little extra video. Hopefully you'll get something out of it, and who knows, it may be helpful to you in the future as well. So I had left off having just defined what a neighborhood around a point is. So we have a metric space. Okay, we talked a lot about that. If we fix a point in the metric space, x naught, and we choose a positive number for a radius, call that p, then the neighborhood centered at x naught of radius p is just all of the other points that are in the metric space that are a distance less than p away from x naught. The classic example using the Pythagorean metric in the plane, 2 dimensions, would just be a disk of any particular radius centered at this point x naught. Okay? But depending on what the metric is, the shape of these neighborhoods can vary. All right? So it doesn't always have to be exactly what you think of in this classic picture here. Okay? But anyway, the concept of a neighborhood is very related to the idea of an open set. You know, we talked about how in the real numbers we have open intervals. That's a very familiar concept. And it's possible to generalize the idea of a set being open to any metric space. So I just want to basically give you the brief definition of that and a couple of examples. So this is the new part for the video. So basically, again, we're going to start with a metric space. So let x and d be a metric space. Okay, and then a subset, okay, a subset, I'll call it U, that is inside of x. So this is a subset of the metric space. This is open. Okay, so we call a subset open if for every point, I'll call it little x, in the open set, in the subset U, right? For every point in there, there exists a radius. I can make up a radius p, right? I can choose a radius. It might be a very small radius, but I can choose a positive number p with the neighborhood centered at x of radius p completely inside of U. In other words, there's one way of thinking about it is there's no points that are on the boundary of U, right? Every point that is in U is sufficiently inside of U that you can make a neighborhood that is around that point that is still inside of U. So if I draw this picture, let's imagine here's capital X like this, all right? An open set, I'm going to draw the boundary dotted, okay, so you'll see why in a minute. An open set U would be something like this, where no matter what point X I pick, right, I can always manage to make a disk around X, right? I can choose a P, maybe a very small number, but I can choose a disk of a certain radius that stays inside of U. And even if I go over towards the very edge of the set U, right, there's always a little bit of room there to draw a neighborhood that stays inside of U. Okay? Now, if you allowed yourself to include the sort of the edge of U, well then points that are on the edge of U would not have this property, right? It would no longer be an open set. So if I had, let me just draw one more picture. If I had made my set U like this, including the boundary, including the edge of the set, then if I pick my point X, notice this has to be for every X, right? If I pick my X right on the edge of the set, then I don't care how small of a disk you draw around that point, it will fail to stay inside of U, right? Part of, you see up here, part of this neighborhood, part of this disk is lapping over to the outside of U. It's too far outside, right? So essentially an open set, you can kind of think of it like this. It doesn't have a boundary. It doesn't have a boundary. So, you know, anytime you have boundary points, like if you can be on the edge of the set, that's not going to be an open set, because any neighborhood around a point that is already sitting on the edge of the set is going to fail to stay inside of that neighborhood, no matter how small you try to make the P, right? So let me give you just a couple of examples of this, a little bit more specific examples. So let's suppose we go back to the real numbers using the absolute value metric, right? Then I would claim that the set U, let's take the open interval from 0 to 1. We call it an open interval for a reason, right? Essentially, here's 0 and 1. Here's my open interval. I'm not including the endpoints, okay? So what does this say then about that subset? In order for it to be open, for every point in that open interval, so maybe I pick my point right here, let's say, okay? There exists a radius that I can make so that the neighborhood, now remember, neighborhoods in this example are just open intervals, right? The neighborhood of radius P stays inside of U. Well, what you're going to notice is that as long as you choose P to be smaller than that distance right there, right, I will have an open neighborhood. I'll have a neighborhood that's inside of the whole set U, okay? In fact, what you can do is if you let, so this, sorry, this should say U is open. That's the claim. That's the claim right there. If I take my point X to be in U, I'm checking this definition now. I'm going to pick a point X that's in U. What I can do, I get to choose what the P is. As long as I can find a P that's greater than 0, I'm going to choose P. So I'm going to measure the distance between 0 and 1 in both directions, and I'm going to take the smaller of those numbers, okay? So I'm going to take the smaller of the numbers 1 versus 1 minus x. So this distance here is x, and this distance right here is 1 minus x. Whichever one of those is smaller, if you think about it, making a neighborhood around x that has whichever of these two numbers is smaller is going to keep my entire open interval with that radius P centered inside of the open interval 0 to 1. Okay? So I'll just say then the neighborhood around x of radius P is completely inside of U. And this is for any x in that interval. Okay? For any x in that interval. On the other hand, I just want to note that if we took, let's say, V to be the closed interval 0, 1, right, then this is not open. In other words, this definition fails because I can find an x. Let's just let x be equal to 0, which is in the set V now. It would not have been allowed to use 0 over here because 0 wasn't a part of the set U. But it is part of V. And now, for any radius that we would try, right, the neighborhood around 0 of radius P will not stay inside of V, right, because this is going to include some negative numbers, right? The neighborhood around 0, right, is going to stretch between negative P and positive P. There's lots of negative numbers in there. So this neighborhood is not contained inside of V. And so this set is not open. I only have to find one point that fails this condition in order to say that something is not open. Okay? So I think that those are the main things I wanted to say. I'm going to ask you to explore these sets a little bit, with the open sets a little bit more in the homework. Let me just see if there's anything else I want to say. There's just a couple of facts here. If you have a metric space XD, then just a couple of facts that are worth knowing. The empty set and the whole set are always open. It doesn't matter what D is. It really doesn't matter anything about that. If you have an empty set or the whole space, it will always be open. The second fact is that the intersection of two open sets is still open, which means you can actually extend this to any finite number of sets, because if you intersect three sets, you can think of it as first you intersected two of them, and then you intersected that with another one, and you just kind of use this fact repeatedly. These are things that you would see proven in a topology class. I don't want to prove them all for you right here, but I just want you to know them in case you see this again down the line. Okay? Finally, the union of any number of open sets is open. So you can take any sorts of unions that you like. They don't have to be just finite numbers of open sets. You could take any number of open sets and intersect them together, and you would get another open set. So those are the main things, I think. Basically, you just need this definition of an open set to kind of finish the homework. Open sets are used a lot when you start defining what a continuous function is. You know, in Math 350, you're going to hear about it in terms of like a technical definition using epsilons and deltas. We don't have that technicality in an abstract metric space or topological space, but we do have this idea of an open set. And the concept of a continuous function can be expressed just using open sets. So that definition was an important one. I thought it was worth it to add a little bit of time to show that to you. I really appreciate you watching the video. I know it's a little bit of extra work. I enjoy making them. I hope that you enjoy watching them. And if there's any questions at all, I can help you with anything. By all means, feel free to let me know. Okay, thanks a lot for watching, guys.